All right, basic antennas. Uh, here's this is some form of Yagi over here. Is that a dual band Yagi, maybe?
Either a dual band or it's the log periodic.
No, it's not a log periodic.
Yeah, it looks like the dual band or band and flight.
Down below it is the infamous J-pole. Uh, down the bottom center is a mag loop, which are becoming very popular. Um, I haven't seen any cheap ones. They run in the four, five, $600 range and up. Uh, on the right is a typical vertical antenna. And this spiral thing up here in the top middle is what sort of a quad thing. I'm not sure.
It's considered a quad.
Where one of these is going to be a reflector.
Yeah, those can be a nice, monomakers. Uh, Dave Lawson has one that's similar to that. Except it's spirals are horizontal and they're turned in opposite directions.
Ah, or you get different polarization.
Uh, Out in the country, a lot of CD are due.
Well, on a quad, depending on whether you feed it on the bottom or a side, determines the polarization. On this, I have no idea what it would be.
But the one that they were showing me, it's like a type of one oil, one side, on the other side. Then you put it in a rim birdhouse, and then you have a stealth antenna.
Okay. All right. So we're going to talk about random wires, dipoles, and verticals. Random wire antennas is just a long piece of wire, randomly long, longer the better. One end of it is usually tied to a pole or a tree, something with some height to it. The other end connects to some form of antenna tuner matching device, which then goes to your transceiver. So, one problem with it, if you're operating with much power, is you're radiating right up at the tuner. And if the tuner is in your shack, you're radiating right there where you're sitting. So it's normally used on low power, QRP type stuff.
They have like you want to have some tuning and grounding, that thing.
Well, I guess you could put a matching transformer outside and get it in.
Nine one six.
But if you do have it coming in there and you have very much power on it, you could get some. You're going to have very high, it's going to be a high impedance at that end. You're going to have very high voltage, so you could get a good RF burn. I haven't experienced that, but from the literature, it says you don't want to experience that.
So I got a very nasty orange through my armpit when I was about 11 years old. On a 40-meter dipole on the roof of our house. And I was redoing the connections on, and my dad did not know I was up there doing it. He came up to the amplifier on CW. Oh boy, did I get a hurt.
You don't do that anymore, right?
I don't do that anymore.
What is a characteristic of random wire HF antenna of a random wire connected directly to the transmitter?
Yeah, things couldn't sorry something.
Yeah, yeah. it doesn't have to be longer than a wavelength. It's a random wire. And it would normally produce horizontal polarization unless you had it going straight up. And I don't, let's see, more effective on lower HF bands than on the higher bands. Depend on the length, wouldn't
Yeah, yeah, well, naturally.
it? I don't know about that one. That's a confusion answer. All right, half-wave dipoles. It consists of two quarter wave elements, usually in opposite directions. You're feeding it at the center. Uh, if it's in free space, of course, there is no such thing. I guess, although if it's on a satellite orbiting the Earth, it's close. It's going to be around 72 ohms characteristic impedance. As you get it down closer to the ground, the impedance changes. And when you get it down very close to the ground, it gets down in the 75 ohm or less range. So 35. It's probably the most common antenna. Most antennas are variations of a dipole. A Yagi or a log periodic are just multiple dipoles set up as reflectors and directors to concentrate the beam because they're still basically a dipole. To calculate the length of the elements, you use our old formula for wavelength, and you throw in the correction factor for the speed of light in a wire. Now, this is typical for like a regular antenna wire. If this was a antenna made out of coax or something, this velocity factor is what they call it. It's going to be different. In some coax, the velocity factor is down like 0.6, very slow. So it makes the length much shorter. So you take the speed of light divided by the frequency and apply the correction factor, and that gives you the wavelength. So when you're doing the dipole, each element wants to be a quarter of that. So it's a half wave dipole, two quarter wave elements. Working through the formula, well, the first one is in meters. Okay, so if you want the wavelength in meters, you take the velocity factor times 300. Okay, so we're canceling out the million to 10 to the sixth. Normally, the 300 million meters per second divided by the frequency in hertz. So if we use the frequency in megahertz, we can use 300.
I was just not used to seeing that on my using the conversion factor 39.45.
Right. Yeah, I just worked through this to show how you get to this other formula. And they normally use it as or represent it as half wavelength in feet, which is approximately 468 divided by the frequency in megahertz. And then in some cases, when you talk about VHF, UHF, they'll want the answer in inches. So you have to apply the 12 inches per foot correction to get inches out of it. So for a half wave dipole at 40 meters, it's going to come out to 65, approximately 65 and a half feet. If you did it without the correction factor, it would come out to like 63.3 feet. So the fact that it, uh, the electrons travel a little slower than the wire, that's why it's a little bit different length. So what is the approximate length for a half-wave dipole cut for 3.55 megahertz? Well, let's see. Now, there's an easy way to do these, and you don't need a calculator, and you don't need the formula. You just have to remember, and you should get to where you can recognize this, that 3.5 megahertz is 80 meters, right? 80-meter band. So if I want a half-wave dipole, half of 80 meters is 40 meters. How many feet are in the meter? A little over 3. So 3 times 40 is pretty close to 132 feet. What's the approximate length for a half-wave dipole cut for 14.250? So this is what, 20 meters? Half of that, 10 meters. Or you can use your calculator and do it quick. Dipole impedance. A center-fed dipole at half wavelength above the ground is going to look like around 72 ohms. It's a decent match without doing anything. You get a 1.5 to 1 SWR with a 50 ohm coax. If you fed it with 75 ohm, you get almost 1 to 1, but you still got to convert it back at your transmitter again. If it was off center fed, where instead of feeding it exactly in the center, if you look at the diagram down here, they're normally fed at 20, 30% offset. And you're running around 200, 250 ohms. And that's where I guess 40, you don't really need a 49 to 1. You need a off center fed. Order lines which are further away from the end. This one's a little bit very close. It's a little bit closer to the end. Those are right. Yeah. And there's no magic number. It depends on where you place it. The impedance is going to increase the closer it is to the end. So when we get to an end fed, where we're feeding it totally at one end, it's going to be 5,000 ohms or more, very high impedance. So the key thing is as you move from the center towards either end, the impedance well, it's not exactly linear, increases to a maximum at the end point. So if you wanted to set it up for 600 ohms, you'd figure out at what position that would be and get a 600 ohm impedance if that's what you wanted to feed it with and you happen to have that sort of matching transformer. So how does the feed point impedance of a half-wave dipole change as the feed point moved from the center toward the end.
Inside. Increases.
Steadily increases. It doesn't linearly increase, but it does increase. Polarization. That's the orientation of the electric field with respect to the Earth's surface. If you remember in the technician information, talked about the electromagnetic wave is composed of an E field and an H field, an electric field and a magnetic field that are at right angles to one another. So since most of these antennas operate on the electric field, we look at the polarization as the orientation of the E field with respect to the Earth. In a horizontal antenna, because the current is going back and forth horizontally, the E field is horizontal to the Earth. If you rotated that wire vertically, then your current is going vertically, and that would be vertical polarization. So it just depends on what plane the current is operating in, and that determines whether it's horizontal or vertical. If you had with a vertical antenna, they're obviously vertically polarized, assuming it's vertical. Now, if you tilt it at 45 degrees, you're going to get a portion of it vertical and a portion of it horizontal, would be called slant polarization. And you could receive it with an antenna that was either horizontal or vertical. Signal strength wouldn't be as good. Yeah, we're not there yet. With a vertical, you have ground waves, but it's mostly absorbed in the ground, not reflected. With a horizontal antenna, which is horizontally polarized, the ground wave, depending on the ground, can be reflected and actually add to the signal and increase the effective gain of the antenna, because you've got the other half of that envelope that's being reflected back up from the ground. Which of the following is an advantage of a horizontally polarized as compared to a vertically polarized HF antenna? Yep. Okay, radiation pattern for a half-wave dipole. If it's in free space, they call it a figure eight. It's actually a donut or toroid around the wire. In other words, at right angles to it. As you get close to the ground, then obviously the bottom half of that toroid would either be in the ground or disturbed. So you start seeing this kind of double lobe pattern. And when you look at over here in the bottom left, if you look at the vertical radiation pattern, you see these two lobes with that cross section. As you lower the antenna below a half wave, it starts to become a big omnidirectional. And the closer you get it to the ground, basically the higher this propagation angle or takeoff angle becomes. And when it's down below, I think they say a tenth of a wavelength, you can do NVIS with it. And that also depends on how good of ground reflection you have under it. In some cases, you can put reflectors on the ground with a real low dipole and get almost vertical radiation. And also it spreads out in a almost circular omnidirectional pattern, where when it's at half wavelength high, you've kind of got two lobes coming out horizontally. What is the radiation pattern of a dipole antenna in free space in a plane containing the conductor? So think of where the antenna is and draw a plane through it. What's the pattern going to be intersecting that plane? I think they could have worded that question better. It's a little.
You explained it up, I was like.
Yeah. Well, I think that's why they threw the plane in there, but it's not obvious. How does antenna height affect the azimuthal radiation pattern? An azimuth is the horizontal plane where it intersects of a horizontal dipole at elevation angles higher than about 45 degrees. And I went back and checked to make sure this is really what that question says in the pool, because I have no idea what they mean by higher than 45 degrees. I know what the answer is, but the question is weird. Maybe they did that so you remember it because it's odd. Well, let's see. Okay, if it's too high, we really hadn't talked about that, it sort of becomes unpredictable. But that's not the answer. It actually becomes yeah, vertically, you keep getting more and more lobes at higher takeoff angles, and eventually you'd get up to the point where they filled in and you'd have that just dome. The height definitely has an effect on the pattern, so that's not it. If it's less than a half wavelength, says the pattern is almost omnidirectional. If it's less than a half wavelength high, the radiation off the ends of the wire is eliminated. Well, that's not true. So it can only be C. And I still don't know what 45 degrees has to do with it. But as you get down close to the ground, you get this
Thanks for bringing this information.
yeah, you get the azimuthal pattern, which is almost a circle.
I enter a 45-degree bank turn on the vertical antenna at 10,000 on the airplane. What is that impedance? Maybe somewhere.
Yeah. Okay, dipole impedance. The actual impedance of a dipole antenna is going to be 73 ohms resistive plus J 42.5 when it's a half wavelength high and it's center fed. So it's going to be or have some inductive reactance. at that height. Now, as you lower it, okay, that impedance is going to decrease. And if you move the feed point, like we talked about before, towards the end, it's going to increase the impedance. So it's approximately 72 ohms in the middle, many thousands at the end, and it varies from between those two, depending on where you are between the middle and the end. On the chart, they're also showing here, these three represent different types of ground and how that affects the impedance. So this was for an 80-meter dipole and showing the heights. So we're down here at the blue line, which is very good soil at 10 meters high, which is an eighth of a wavelength, is down a little over 40 ohms. And we get up to about 95 ohms out here at 26 meters high, which is pretty high. How does the feed point impedance of a horizontal half-wave dipole change as the antenna height is reduced to 1/10 wavelength above ground? It decreases. Vertical antennas, they say the second most popular. They have a very small footprint. If you have a confined space and you can't run a long wire 80-meter antenna, so all you got is a condo balcony or something, you can stick up a vertical antenna.
You're getting Christmas tree if you're HOA.
Right. Hang a birdhouse on it or something, and yeah. They're a little easier to disguise, easier to use, much less gain than the dipoles and any of the beam antennas. They do have a omnidirectional radiation pattern, and it is also affected by height. The takeoff angle, which is what you see over here, if you look at the elevation plot over on the right, the takeoff angle is the angle at which you get the maximum radiation in that lobe. So in the one they're showing there, it's about 30 degrees. As you raise the vertical, that takeoff angle lowers, and you get down into the maybe 15, 20 degrees with it up at the right height. Over here on the left, we're showing a typical like quarter wave vertical, where one side is of the coax is tied to the antenna, and the shield is grounded or through ground radials acting as, I guess, a counterpose, poise in that case, where it looks like the other half of the antenna. So in order to figure out the length of that quarter wave antenna, we take our other formula in where we did it in feet for a half wave and just divide it by 2. So it's 234 divided by the frequency in megahertz. And that'll give you the length of your quarter wave antenna in feet. Which of the following best describes the radiation pattern of a quarter wave ground plane vertical antenna? Yeah, now they just said the radiation pattern. They didn't say azimuthal or elevation wise.
You did say you missed it.
Omnidirectional and azimuth. Looks like a perfect circle. Whereas, remember when we got the dipole down low, it still had some squish where the radiation pattern towards the endpoints of the wire were less than it was perpendicular to it.
Not counting metal structures around. And still there.
Yeah, this assumes that there's nothing else around. Like Dave Castor says, with antennas, everything affects everything. And then some. What is the approximate length for a quarter wave vertical cut for 28.5 megahertz? Now again, 28.5 megahertz is what? 10 meters. Is that a clue? So a quarter wave of 10 meters is 2.5 meters. And by my math, that's about 8 feet. Or you can use your calculator. Or you can write down the equation with your pencil. It's easier just to figure out what the wavelength band is and then just estimate it. Quarter wave vertical ground plane antennas. So it's essentially a vertical dipole, and the bottom half of it becomes ground radials. So you've got a quarter wave sticking up in the air, and you've got the other quarter wave essentially underground or on the ground as radials. And normally, the radials are either laying on the surface or can be buried a few inches. I haven't seen anything on how far they can be buried. I did see a video from this little Russian girl that does a lot of YouTube stuff, and she was at some beach over in Russia and took a dipole and buried it on the beach several inches under the sand, including the feed line, and made a whole bunch of contacts. It was weird. That common knowledge said that shouldn't have worked. Where should the radial wires of a ground-mounted vertical antenna system be placed? See, does it make any difference if it's insulated wire or bare? Okay. Vertical antenna impedance for a quarter wave vertical. If you have your radials horizontal, they do not contribute to the radiation pattern. So you wind up with a feed point impedance of basically half what that would be if it was a true dipole oriented vertically. If you raise your vertical antenna and it has radials, and a lot of them you buy have actually 4 or 8 radial wires sticking out of them at an angle. When they're sloped down at 45 degrees, you can get approximately 50 ohm impedance. So that's why they do that on a lot of the commercial radials, and you don't really need a matching transformer or tuner. You're still stuck with the fact that it's a uh, much less gain than you're going to get with a dipole, with a normal dipole. And I guess they tend to pick up more noise than a horizontal. Because as I understand, most man-made noise is vertically polarized. I don't know why, but that's seems to be the case. Which of the following is a common way to adjust the feed point impedance of a quarter wave ground plane vertical to be approximately 50 ohms? Sloping at 45 degrees. Now, that other one, uh, they say if you have your radials vertical, and I'm assuming that would be up in parallel with the antenna, it becomes a vertical dipole. Not exactly sure how that works myself.
Vertical dipole.
Yeah.
Like a J-pole.
Well, a vertical dipole, I guess what's confusing me, they say vertical for the radials, they'd have to be straight down for it to be a dipole. The way they word that makes me think that they're up in parallel with the antenna, which wouldn't work at all.
Yeah, that would cause very might make it a vertical feed. And it would mention the little cancellation.
Yeah,
Nice.
I would think you'd get kind of nothing out of it. Okay.